So I remember when I took introductory physics, when we did the section on springs, I just couldn't imagine a more mind-numbingly boring topic than springs. And I was just kind of wondering, like, who cares about this? And then it turned out, you know, years later, I realized, oh, that was actually the most important section of that course and was the foundation for everything I did in all of my later studies. So I want to try to be careful to explain a little bit of what the spring force really means and why it's something that is studied in introductory physics course. So we present springs as being these like metal coils that are in your mattress or whatever. But really, we have a much more general idea about what springs are in physics. Namely, all materials behave like springs. This is because basically the interaction between atoms is often very spring-like. When you have an atomic bond, we like to think of atomic bonds as being almost like a little spring connecting the two atoms. If you push the atoms together, they'll try to bounce back. And if you stretch a bond, it'll try to snap back this way. So since all of the atoms, you know, in any structure or in your body are spring-like, that means that every object is also spring-like, and everything that makes your body up and all the objects around you are also very spring-like. What I mean by that, practically speaking, is that materials can exhibit both tension and compression forces, and the magnitude of these forces follows the same basic formula that springs do, namely F equals kx. The only difference is we switch up our terminology a little bit here. First of all, K, the spring constant, is not so convenient for describing real materials because it's much more convenient to have a parameter that depends only on what a material is made of and to be able to explicitly put the size and shape of the material in there. So K is replaced by an expression, let me write it with the pen. K is replaced by an expression, we're going to use capital Y times A divided by L subscript 0. And I'll have to explain what each one of those means. Okay, Y is called the Young's modulus, also known as the elastic modulus of the material. This is one of the main parameters they use in the world of engineering to describe what a material is like. So you can look up online if you want to, what's the Young's modulus for wood? What's the Young's modulus for concrete? What's the Young's modulus for steel? What's the Young's modulus for bone? And you can find how these different materials behave in the same sense as the spring constant. Like, you know, if you take a steel bar and you stretch it, and then you take a bone and you stretch it, which one will provide a stronger force to pull it back together? That's what the Young's modulus is telling you about the material. A is the material's cross-sectional area, where the cross-section is taken perpendicular to the force F. So in other words, like in my example, imagine you take a steel rod and you try to stretch it out. If you have a very, very thin rod that's like a piece of wire, basically, it'll be easier to stretch than if you have a big, thick steel rod. So that's the A. You know, if A is very small, it would be something like a piece of wire. If A is very big, it's like a huge support beam. And then L, oftentimes we use L subscript 0 to emphasize what I'm about to say. L is the material's rest length, basically. It's analogous to the rest length of the spring. It's the material's length when it is not stretched or compressed. So in other words, a very, very long beam is going to be easier to stretch out than a very short beam, which I think you can sort of understand. If you picture like a rubber band, one that's really, really long, you have to apply less force to stretch it than one that's extremely short. Okay, so anyways, that expression plays the role of the spring constant. And then normally in this business, instead of X, we usually replaced it with delta L, which the meaning of that is pretty obvious. Final length minus initial length. So that's the change in the object's length. So in other words, that has the same meaning as X, basically, because X, remember, is the change in length from the rest length to the actual length. That's the same thing that delta L means. So it's really just a different variable that's representing the same idea. So if we put all that information together into the equation, then the equation we end up getting is F equals Young's modulus times cross-sectional area divided by L0 times delta L. And that is basically our F equals Kx for real materials. More commonly, the way people write this is they put F over A on the left-hand side of the equation, and then they put Y here, and then they put delta L over L like this. So this is just a simple algebraic rearrangement of the variables. And the reason they do that is just because these are kind of the more practical quantities to deal with. F over A is referred to as the stress on a material. So it's the force divided by the cross-sectional area. And then over here, delta L over L, this is referred to as the strain on a material. And just notice, by the way, that the strain, it's a length divided by a length. So the strain has no units. So what you might see in practice is something like, somebody might say the strain is, somebody might say like that the strain is 1% on the material. A 1% strain would mean delta L over L0 is 0.01. So in other words, the change in length is 1% of the rest length. That's what that statement would be telling you. So I just wanted to mention that because sometimes you'll see it presented that way in problems and stuff like that. You'll see the strain quoted in percentages. So just know that that percentage is delta L divided by L0. So oftentimes, if you ever see this again, especially in the world of engineering, you'll probably hear it talked about in the context of stress and strain. So if you hear about stress strain curves, just remember that that is actually F equals Kx, just with a bunch of, kind of obfuscation layered on top of it. But so anyway, the final punchline is that you can treat any material around you in the world as being like a spring. And that actually has huge implications for engineering, on building bridges and buildings, and on how the human body works, and on how different machines work, and vehicles, and lots of things. This is one of the main things that they have to think about in engineering when thinking about what materials are suitable for different tasks.